Okay, so today we'll study sound. These are mechanical waves. What does that mean? They need a medium to travel in. Okay, so sound won't propagate through vacuum. You know. In solids, they can be both longitudinal and transverse. Okay, I forget what longitudinal and transverse means. Anybody remind me of that?
Longitudinal is in a parallel axis, transverse is perpendicular.
So longitudinal, right? The particles of the medium are oscillating parallel to the direction of travel of the wave. In a transverse wave, particles of the medium are oscillating perpendicular to the direction of travel of the wave. Okay, so in a solid, you can have both longitudinal and transverse waves, sound waves. In fluids, what are fluids?
Yes.
Liquids and gases, you can only have longitudinal waves. Okay. So the sound waves getting to you are traveling through air, so those are longitudinal waves. Okay. So let me show you these waves before we get into the slides. Okay, so here's how you produce sound waves. You can use a diaphragm and make the diaphragm oscillate. And what it does is, it creates a high pressure, low pressure, high pressure, low pressure region. And that pressure wave travels to the right. So the wave is traveling to the right. And if you looked at each particle, if you concentrate on each air molecule, so you see the air molecule is oscillating like that. Okay, so that's a longitudinal wave. Here's a transverse wave. Okay, in a solid, see the wave is traveling in this direction, and the solid particles are oscillating in this direction. Okay, this is a transverse wave. All right, so again, in solids, you can have both longitudinal and transverse waves. Okay, so you can think of seismic waves. What are seismic waves?
Earthquakes.
Earthquakes traveling through Earth. You can think of them as sound waves. Okay? And they're both longitudinal and transverse. Okay? Their speed depends on the medium. So for instance, earthquake waves, longitudinal waves are faster. Okay? Transverse waves are slower. All right. Those are known as primary and secondary waves. Okay. Right, so sound waves is what we're going to travel. We're mostly going to concentrate on sound traveling through air because that's what we experience most of the time. Okay, but it'll apply to most everything we're saying. All right. So we'll talk about the Doppler effect. We'll talk about the intensity of the sound. Intensity tells you how much energy is reaching you per unit area per second. Okay, when the sound gets louder, the intensity is higher. Okay? But you'll learn an interesting fact about that. Okay. We'll talk about shock waves and so on. Okay? We'll come to this diagram in a little bit. Okay. So, like I said, any vibrating stuff, a vibrating diaphragm, can produce sound waves. Okay. So for instance, here's I'm waving my hand and I'm producing sound waves. Why can't you hear that?
Low intensity.
The frequency is below what you can hear. Okay? So you can, in principle, you can hear about 20 hertz, but this is way below 20 hertz. Okay? So this is an infrasonic sound. Infra meaning below the frequency you can hear. Okay. So when you vibrate a diaphragm, about 1% of the speaker's energy is converted into compressing and expanding the surrounding wave. about 1% of the energy goes into producing sound wave. Okay. So a 100-watt speaker is using 100 joules of electricity per second, and it's, what is the sound? How much energy power is going into the sound? 1 watt. All right. Sound waves are in most fluids are longitudinal because fluids have no shear strength. In solids, they can be both transverse and longitudinal. All right, so here's a piston, and here's an air column. You can pump the piston, make the piston oscillate, and it'll produce a pressure wave, high pressure, low pressure, high pressure, and this wave travels to the right, okay? So you see the pressure, this is a high pressure, that's a low pressure, that's a high pressure. Okay, so this is atmospheric pressure. And on top of the pressure, atmospheric pressure, you're increasing and decreasing the pressure to produce a sound wave. You saw that in this sound wave, molecules were oscillating, air molecules were oscillating like that. So what this diagram is telling you is these molecules are moved to the right. These molecules are stationary. These molecules have moved to the left. So these molecules moved to the right, these guys were stationary, and these guys moved to the left. That's how you have a higher pressure there. Okay? Anyway, so this is the motion of the molecules, this is the pressure wave. Okay? So here's the pressure wave, this is represented as, that's the maximum pressure, okay? And sine kx minus omega t. K is the wave number, omega is the angular frequency. Okay? The pressure amplitude, again, you don't have to remember any of this stuff, is the density of the fluid. So if the sound wave is traveling through air, that's the density of air. If the sound wave is traveling through water, that would be the density of water. That's the velocity of the wave, that's the angular frequency, and that's the amplitude of the particles that are oscillating in the medium. Okay? So in fluid, sound waves are longitudinal waves. Sound waves travel through any material medium. Okay. Their speed depends on the property of the medium. Okay. In general, stiffer the medium, faster sound will travel. Okay. So here's a wooden table. Sound travels through this wooden table. Yeah. Now, if this was a steel top table, what do you think will happen to the velocity?
Maybe higher.
It will be faster. Okay. All right. Okay. Have you heard of the term wave fronts? All right. So let me show you a wave front. Okay. Okay, so this is a ripple tank. There's an oscillator hitting the water. And you see when it hits the water, it's creating a crest. And all these crests that were created at the same time, that's a wavefront. Why do you think we talk about the wavefront? What do you think the wavefront is giving you? Okay. What its energy travels perpendicular to the wavefront. Okay. All right. So wavefronts are crests created at the same time, okay, and energy travels perpendicular to the wavefront. If you have a point source, okay, like the sun, okay, the sun is not a point source, but if you're far enough, it creates spherical wavefronts. Okay. These are circular wavefronts. When the circle becomes very large, you can already see that these look like plane wavefronts. That's what happens in the ocean. Okay, when you go to the beach, what you're seeing is a line of crest coming at you. Yeah. All right. So you can have all kinds of shapes, but the energy is traveling perpendicular to the wavefront. Okay, so planar, circular, and spherical wavefronts, among other shapes, are possible. Okay. So we categorize sounds based on how our sensor works. Okay, the sensor that you're born with. Okay, audible range, audible waves, you can hear in principle from 20 hertz to 20,000 hertz. Okay, now I probably can't hear stuff about 8,000 hertz, but and probably below 80 to 100 hertz, and maybe 80 hertz. Okay. And then here's something. Teenagers can hear frequencies of 10,000 hertz and above, but I can't hear them. Okay. So now let me tell you a real world application of this. Can you think of any useful? Why are we talking about this? Why would this be useful?
Subliminal messaging?
So no, you go to a mall, an expensive mall, and go to a store where they have a lot of expensive stuff. They don't want teenagers coming in there. Yeah, so they just play a high frequency sound, annoying high frequency sound, and they can keep the teenagers out. The one people with money, they can't hear it. So, all right. So next time you go to a store and you hear a high, annoying pitch, you know what's going on. All right. So I mean, this was during the old days. Nowadays, bandwidth is cheap, so it doesn't matter. See, human voice ranges from 80 hertz to 14,000 hertz. Yeah. So back in the old days, the telephones would cut off at 3,500 hertz. Okay, so if you had a opera singer, their voice would be cut off. I mean, they couldn't sing to you over the phone. But nowadays, they'll transmit up to 7,000 hertz because bandwidth is cheap. Okay, so here's an interesting question for you. Okay. So we can produce sound in that frequency range, up to 14,000 hertz. Why do you need to hear up to 20,000 hertz?
You say why?
Yeah, so you're producing in one range. You're producing sound in 80 to 14,000 hertz, but you can hear in this range. Why can you hear in a wider range?
Other animals.
There you go. Okay, so you have to survive in an environment. Okay, so you need to be able to hear in that. So infrasonic waves are waves of frequency less than 20 hertz. Ultrasonic waves are waves of frequency higher than 20,000 hertz. Okay. Remember in the lab we were using an ultrasonic motion sensor. Okay. So it was using sound waves of frequency higher than that. Okay. You guys following this? Speed of these sound waves. The speed of the wave depends on an elastic property. Elastic property is, you saw that in one of the shear modulus, Young's modulus, and bulk modulus. So transverse waves will depend on shear modulus, and longitudinal waves will depend on bulk modulus. Okay? And then the inertial property, which will be the density of the medium. Okay. So for longitudinal sound waves in solids and liquids, the velocity is the bulk modulus divided by the density of the medium. So in air, okay, so the temperature in this room is about 20 degrees Celsius, and the speed of sound is 343 meters per second. So sound will travel from here to Mainland High School in 1 second, roughly. Okay. In water, see, it can travel almost 5 times as fast. In steel, in iron, it travels almost 20 times as fast. Okay. All right, so we will be interested, see, you can see that from here. So this is the speed of sound in air. At 20 degrees Celsius, it's 343 meters per second. At 0 degrees Celsius, it's 331 meters per second. That's about a 3% increase. Okay. So the speed of just sound changes with temperature, and this formula gives you the change in speed of sound in air with temperature. Okay. Gamma, you'll learn about this in the next chapter. Gamma is the ratio of specific heats. Okay. It's this is molar specific heat of air at constant pressure, molar specific heat of air at constant volume. Okay. So that's if you're dealing with air. Okay. That's the gas constant. So here's the velocity as a function of temperature. This is in Kelvin scale. Okay, so if you put the temperature in Celsius scale, there's the velocity of speed of sound as a function of the Celsius temperature. And this formula is simplified here. It's at 0 degrees Celsius, it's 331 meters per second. And for every degree rise in Celsius temperature, the speed increases by 0.6 meters per second. Yep.
How is the speed going up as temperature goes up? Surely as temperature drops, it gets denser, speed go faster.
Okay, so the density went down, the bulk modulus went up. Well, the density went down, that itself probably would account for a speed increase.
I had it backwards though.
Mm-hmm. All right. I hadn't thought of it, so probably just the density change is enough to increase the speed. All right, so you might have seen this. Okay, sound travels at 343 meters per second, that's 0.3 kilometers per second. And light travels at 300,000 kilometers per second. So almost 1,000,000 times faster than sound. Okay. So here's the rule. You always see the flash of lightning first, okay, and then you hear the thunder. So if you hear the thunder 5 seconds after you see the flash of lightning, then that's a mile away. If you hear the thunder 10 seconds after you see the flash, that's 2 miles away. Okay. And of course, if you see the flash and hear the thunder at the same time, that's probably the last thing you did. Yeah. What's that?
I almost did get struck.
Oh yeah?
Yeah, I was out when I was over the road with my dad, and I was checking out the truck and stuff, and then it cracked right by me, and I was scared for a while.
Oh yeah, I would imagine. So how far away did it strike? Did you?
Maybe a couple hundred feet,
Oh, wow.
but it was loud.
I bet it was. All right. All waves carry energy. Okay. So sound waves carry energy as well. Okay, so here's this piston which is vibrating and it's sending waves down this tube. All right, and we want to know, we'll stand someplace there and we want to know how much energy is passing us per second. Okay, and that'll be the power. Okay, so what's happening when you make the piston vibrate, you're pumping energy into the system and that energy is traveling away. Okay. Of course, if the energy didn't propagate, it would all remain there, and that's, but the sound wave takes the energy away. Okay, the wave carries the energy away. So the power, that is how much energy is passing you per second. The power is 1/2 rho. What is rho? That's the density of the medium in which the sound wave is traveling. A is the area of cross section. Okay, V is the velocity of sound. Omega is the frequency. Okay, and see, faster this thing is oscillating, greater the power that's being transmitted, and S is the amplitude of the air molecules, so the particles that are vibrating. Okay, and the power is dependent on the square of these guys. Intensity is the power per unit area. Okay, so intensity, so if this is 1 meter square, 1 meter square is roughly the size of that table. Okay, so you got to cut it and make it into a square. 1 meter square is that much. So 1 meter square, intensity is the energy passing 1 meter square per second. Okay. That's the intensity of sound. Now, it turns out that you increase the intensity of sound, it sounds louder. But it turns out that you double the intensity, it doesn't sound as twice as loud. And we'll come to that in a second. Okay? All right, so intensity is power per unit area. And in terms of the pressure amplitude, it's pressure amplitude squared divided by 2 density in the medium times the velocity of sound. So intensity of a point source, this could be a little birdie singing, and if it's projecting in all direction equally, the intensity at a distance r is the power divided by 4 pi r squared. What is 4 pi r squared? What is this? What's that? That's the surface area of a basketball. That's the surface area of a sphere. Okay? All right. So that's the intensity of the sound from a point source at a distance r. It falls off as 1 over r squared. Okay. All right, now let's come to the intensity. Intensity is the energy passing per unit area per second. And that's intensity. Yeah. Energy per unit area per second. Okay. All right, so let's most people are surprised when they hear this, but let's do this. Okay, so our friend here is playing a piano or a violin. I want you to hear it twice as loud. What do we need? Huh?
You want me to make a sound or something?
No.
Oh, okay, sure.
No. So, what will we need to do if I want to hear it twice as loud? Get 2 people to play?
You need to 10 people.
10 people. Okay, so most people don't know that. Yeah, I want to hear it twice louder than that.
100.
100. Okay, so that's why those orchestras, have all those violinists and so on. So they can have a loudness range. Okay. So the intensity has to increase in general by a factor of 10 to hear it twice as loud. So that's why we define the decibel scale, okay? So it turns out that your sense of loudness increases with X, not with intensity, okay? So your sense of, your perception of loudness increases with the power with X here, okay? So you take the logarithm of the intensity, log of the intensity, and you get X. Okay? And so we define something called a decibel scale. The decibel scale is 10 times log of intensity divided by I naught. I naught is the threshold of hearing. That's the lowest intensity you can hear. Okay? So when the sound level, decibel level increases by 10 decibels, that is, the intensity is increased by 10, by a factor of 10, and you hear it twice as loud. Okay. So humans can detect intensities in the range 10 to the minus 12 watts per meter square. So that is the softest intensity you can hear. That is I naught. And 1 watt per meter square. So that's the loudest you can bear to hear. That's a trillion folds. And the loudest sound you can bear to hear is not a trillion times louder than the softest sound. Okay? So your sense of loudness doesn't go linearly. Like I said, it goes like X there. So it turns out that the softest sound you can hear, the loudest sound you can bear to hear is about 5,000 times louder than, okay, not a trillion times louder than the softest sound. All right, so that's why we define the decibel scale. So threshold of pain is 1 watt per meter square, and on the decibel scale, it's 120 decibels. Okay? Threshold of hearing, the softest sound you can hear is 10 to the minus 12 watt per meter square, and it's 0 decibels. So an increase in sound level by 10 decibel corresponds to increase in sound intensity by a factor of 10. Okay, so if you have a 5 dB sound, 15 dB will sound twice as loud. Okay? So 25 dB, 35 dB will sound twice as loud. Okay? So here are some sounds in decibel levels. Okay, you don't want to be standing next to a jet airplane. That sound intensity is 150 decibels. A rock concert is 120 decibels. I guess it's not a good idea to pay $500 to be next to the stage or next to the speakers. Okay, leaves rustling is 10 decibel. Okay. So again, as a rule of thumb, doubling in loudness is approximately associated with an increase in sound level by 10 decibels. Prolonged exposure to high sound levels can damage your ears. In addition, they can contribute to high blood pressure, anxiety, and nervousness. So it's not good psychologically as well. So this sensor that you're born with, what does this guy do?
Interprets sound.
What does this guy do? So it converts mechanical energy to electrical energy, right? It converts sound waves to nerve impulses. Yeah. It has tremendous range and sensitivity, so you saw that you can hear from 20 hertz to 20,000 hertz. Okay. It can tell you the frequency of the sound. It gives you information about the intensity of the sound and the direction in which it's coming from. How do you tell the direction it's coming from?
You have 2 ears.
There you go. So just like two eyes and stuff like that. Okay. If the sound is coming from here, this reaches that ear first and then there later. And that time difference, you can tell where it's coming from. Okay? Now, if it's a low frequency sound, it came here and that low frequency comes there like that. Okay. If it's a high frequency sound, this came here and this, as long as the wavelength is smaller than your head, it'll go through your head. Okay. So when it goes through your head, what happens to this intensity?
Slightly less.
It's a lot less, and that's what you take rather than the time difference. Okay. All right. So you have directional information, you have pitch information, and you have intensity information. Okay. The pitch information, your brain, your computer, is smart enough to tell. It can tell 0.3% difference in pitches. Okay. So if one sound is 500 hertz, 0.3% difference is 501.5 hertz. You can tell they're different pitch. Okay. So if it's one is 100 hertz, okay, 100 hertz and 100.3 can be, okay, you can tell the difference. So the perception of intensity is loudness. You can discern differences of 1 decibel. So you can tell 10 dB, 11 dB is louder than 10 dB. I mean, it is louder, but you can tell that. Yeah. And 3 dB is easily noticed. Yeah. Now, our perception of loudness depends not just on intensity, it depends on frequency as well. Okay, it depends on intensity and frequency. So let me show you a graph. So here's a graph. This is the font. So when you go to a doctor's office, when you were kids, they would test your hearing. Okay? And so what they're doing is they're testing at different frequencies. Okay? So if you used an instrument, an electronic instrument that responds at the same frequency, see, let's say an instrument says all this is 20 decibels. But for you, this is 20 decibels. See, it has to sound 40 decibels at that frequency for you to say it's 20 decibels. You see, it has to sound almost to 80 decibels at that frequency for you to say 20 decibels. Okay. So your ear is not responding the same way to all frequencies. Okay. So this is your perception of loudness. Okay. So this is 0 phon. Okay. So this is, you can barely hear this. Okay. So at 40 hertz, it has to be fairly loud before you can hear it. You're most sensitive to the frequency 3,500 hertz. Okay. That's what that is. All right, so by definition, at 1,000 hertz, you and an instrument agree at all frequencies. Okay, so that's how the thing is defined. So here are some of common sounds that you hear. Okay, again, this is the white range is what you can hear. Okay. Like I said, at lower frequencies, the sound has to be fairly loud before you can hear it. Okay, at these frequencies, it's got to be almost 120 decibels before you can hear it. You know? So the instrument is going crazy at that frequency, and you can barely hear it. Okay. So there is the sound level at school cafeteria, birds, whispered speech, urban traffic, motorcycle. You can see what's annoying. Underwater communication, those are sonars. Bats, a lot of bats use echolocation. What does echolocation mean?
Oh, it's they make a high frequency noise, bounces off
Mhm.
whatever they're looking at, and returns to them, and they turn that in their ears.
Mm-hmm.
But my question is,
Mm-hmm.
why are some of them, like large rocket engine, the top left,
Mm-hmm.
why is it in both? Are you saying that,
Oh, it produces a range of frequencies.
so at its lowest frequency,
Mm-hmm.
at the highest decibels,
Mhm.
you won't be able to hear it?
Yeah. Mm-hmm.
Okay.
Mm-hmm. But you can feel it. All right. Okay, we'll come to echolocation later. All right, so those are yeah. Large animals can hear low frequencies. The reason being low frequencies travel a longer distance. Okay, so for instance, if you're an elephant, you're large and you need to eat a lot of food, so you need to cover a lot of ground. So you need to be able to tell your buddies, hey, there's good food here from a long distance. Right? So, all right, now we'll look at interference of sound waves. What is this?
Noise canceling?
So when multiple sound waves are traveling, what happens at a given point? Okay, so let's look at that. All right, so let's say this is simulating it. All right, so you're producing two sound waves. Okay, so you can think of these as two speakers, and they're sending out sound waves. This speaker is sending us sound wave. Let's slow down the simulation. This is sending sound wave, that is sending sound wave. And you see along those lines, both the sound waves are coming and canceling each other. Okay, that's destructive interference. And along this direction, they're adding together. That's constructive interference. Okay? Constructive interference, destructive interference. Okay? And so in a theater, you see that they put aisles in certain locations. That's where the destructive interference happens. Okay? So as an audio engineer, you have to figure out all of that. Okay? All right. So here is a speaker, here is a speaker. This wave travels that distance to get to that point, and this wave travels that distance. Okay? Now the point is the following. If one wave reaches with a crest and another wave reaches with a trough, that point, they will cancel each other and you'll have destructive interference. Okay? So if one wave reaches with a crest and another reaches a trough, you have destructive interference. If both reach with a crest, then you have constructive interference. Okay. All right, so what this is showing you is a purely constructive interference. So the wave from here to there and the wave from here to there reach with crests, so you have constructive interference. Constructive interference, constructive. Purely destructive. Purely destructive is they exactly cancel each other. Okay. All the black spots are destructive interference. Yeah. So the interference, what you'll get will depend on this. So there's the distance that this guy traveled, there's the distance this wave traveled, and this is assuming if they start with the same phase, okay, they're starting in similar fashion. If this started with a crest, this guy is starting with a crest. Okay, this is the path difference, the difference between this distance and that distance. So this is R2 minus R1. And that's equal to, this is the wavelength divided by 2 pi times phi. Okay, so if here, if the path difference is n times the wavelength, then you'll get constructive interference. If the path difference is 1/2, it's an integer plus half times wavelength, then you'll get destructive interference. All right, so here's a device that will illustrate this. Okay. So you play a pure tone through the speaker, and as you move this arm up and down, what will happen? There's a wave traveling like this, and there's a wave traveling like this. So as you move this arm up and down, what will happen?
The relative distance traveled for the upper arm will change,
Mhm.
so you'll have periods of noise canceling.
There. So you'll have constructive interference and destructive interference. Okay. Now we'll talk about the Doppler effect. What is the Doppler effect?
It's sound wave stacking. Or, yeah.
Okay, so here's a source that's producing a frequency. Let's say it's producing 300 hertz frequency. Now, if you move towards the source, you'll hear a sound that is of higher frequency. If you move away from the source, you'll hear a lower frequency. That's the Doppler effect. So the perceived pitch is different than the produced pitch if there is relative motion. And that happens if the source moves towards you. If the source moves towards you, you hear a higher pitch. And you've all experienced this. When an ambulance siren is coming toward you, you hear a higher pitch. And once the same ambulance goes by you, the pitch is lower. Okay, that's the Doppler effect. All right, so let me show you how this thing is happening. Okay, so here's a stationary source, and if you're standing here, the frequency is, let's say it's producing 100 crests a second, and if you're standing there, 100 crests a second will pass you. Okay, so the pitch you hear, if both are at rest, the pitch heard is what is produced. Now, if the source is moving and you're here, if it produces 100 crests, more than 100 crests will pass you if you're standing there, and less than 100 crests will pass you if you're standing there. So here you'll hear a higher pitch, here you'll hear a higher frequency, here you'll hear a lower frequency. And that's the Doppler effect. Okay. When observer and source move toward each other, the apparent frequency is higher than the emitted frequency. Okay? And if they're moving away from each other, then you hear a lower frequency. Yeah. Okay, so here's the perceived frequency, F prime. F is the emitted frequency. V is the speed of sound in the medium. V0 is the speed of the observer. Again, V is the speed of sound, which is 340 meters per second, roughly. This is the speed of the source. Okay. And there's a sign convention. If the observer and source are moving, velocity are positive when they move toward each other. These guys are positive when you move toward each other. Okay. So let me do some examples. Here's the source, here's the observer. Let's say if the source is moving at 10 meters per second, then the observed frequency will be V plus 0, observer is at rest, V minus 10 times. Okay, so this frequency will be higher. for this case, f prime will be v plus 10 divided by v minus 0. Frequency will be higher. Okay, will this be will you hear a higher or a lower frequency?
Higher.
Higher frequency, okay. Okay. All right, so as long as there is relative motion toward each other, you hear a higher frequency, and if there's a relative motion away from each other, you hear a lower frequency. Okay? That's the Doppler effect. What if you move faster than the speed of sound? If the source, the object that's producing the sound, then you get what is called a shock wave. Okay, so this is illustrating this. Okay, so you hear, here is the source. Okay, so what this diagram is showing you is the following. The source, when the source was here, it produced sound, and after a little while, after time t, the source has traveled to that point, but this guy is traveling faster than the sound, and the sound has only traveled to this point. Okay, so the sound has traveled that far. The source has traveled further, is gone past that. And when the source was here, the sound it produced has traveled there, and the source is there. So what's happening is, see, all the crests are lining up on the surface of a cone. The crests are high pressure regions. So what is happening is, this is atmospheric pressure, this is high pressure, and this is atmospheric pressure. So as you grow across the surface of the cone, when you hit the surface of the cone, you get a high pressure spike. Like that. Okay, so here's a cone. So here's a plane flying. This is the shock wave. Okay. This is all atmospheric pressure, pressure spike, atmospheric pressure. Mm-hmm.
How does that work for a transverse wave? If the, like, for example,
So water waves are sort of sum of longitudinal and transverse wave. And so that wake that you see on the boat, that's a shock wave. So if the water is shallow, the speed of a wave on the surface wave depends on the depth of the water. And if the water is shallow, the boat is going faster than the speed of the wave on the water. And that's a shock wave. Yep. This is called the shock angle. Sine of that thing is the speed of sound in the medium, and this is the speed of the source. Okay, so you see this thing has a solution as long as the speed of the source is greater than that. Okay. Mach number tells you how much faster than sound you're traveling. Okay, so Mach 2 is you're traveling twice the speed of sound. Mach 3 is 3 times the speed of sound. See, there is a shock wave. Yeah. Jet will produce 2 shock waves. One, the nose cone produces one, and then the tail produces one. Okay? So as this thing is going, there's a shock wave. This person hasn't heard anything yet. This person has heard one boom. This person has heard both the sonic booms. Yeah. Yeah.
Why is the tail section generating its own shock wave?
I don't know. Mm-hmm.
it's the end of the source. What the jet is the thing that's pushing air out of the way. So when it's gone, it just collapses. There's nothing pushing it anymore.
Mm-hmm. All right, so anyway, so it produces two shock waves. So the speed of sound is 750 miles an hour. Okay. All right, let's see. Oh, yeah. You guys seen this picture? This one? Do you know what that is? Okay, so let's see. Okay, so the pressure profile actually across this thing is like so. There is atmospheric pressure, high pressure, and then you get a low pressure spike, and then like that. Okay, so again, this is atmospheric pressure, high pressure spike, and then low pressure, and then like that. Okay, when the pressure decreases, what happens? Air expands, okay? It cools down, and the water, if there's moisture in there, it'll condense, and that's what that is. So where is this thing? Anyway, go watch the movie. So from the angle of that thing, you can calculate the speed of the plane in principle. Okay. All right, now we'll look at musical instruments. Musical instruments produce standing waves so when you pluck a string, a wave travels like that, and an identical wave is reflected. And what you do is the string, what you excite is standing waves. Okay, so here is a string, and this is the lowest frequency at which it can vibrate. Okay, so you see this is an antinode, that's a node. An antinode just means these particles are oscillating with the greatest amplitude. These particles are not vibrating at all. This is the next higher frequency, and if this is F1, this is 2 times F1. This is 3 times F1, okay? So they form a harmonic series. Okay. So this has 2 antinodes and 3 nodes. 3 antinodes and 4 nodes. Okay. So the frequencies at which the string can vibrate are n times v, the speed of the wave on that string, and that speed is the tension in the string divided by mu. Okay. So n times n over 2l. Okay. So n is an integer. Okay, it takes all integer values. 2l tension in the string divided by the mass per unit length. Okay, so when you're playing the guitar, the way you produce all different frequencies is, well, you have 6 different strings, so you have 6 strings to choose from. Well, the tension you have set at the beginning, so you can't change that. You can change between 6 strings, and then you can change the length of the string by pressing down on the string. And different, okay? So the lower the length, higher the frequency it produces. Okay? So that's the kind of, that's the control you have. Yes, so when playing an instrument, it's difficult to excite a single mode. So normally when a string is plucked, various harmonics are excited. When you pluck a string, a mixture of all these guys are excited. When you play an instrument which has pipe open at both ends, such as a flute, okay, the frequencies this is the lowest frequency you can excite. You can see that this is an antinode at the ends and node there. Node, antinode, okay? And actually the antinode sticks out a little. Okay, so the frequencies you can excite, You can excite all harmonics, V over 2L. Okay. The expression is just like that for a string. Okay. If you have a pipe that's closed at one end, okay, you can only excite the odd harmonics. So this is less versatile than a pipe that is open at both ends. Okay. So for instance, a harmonica has little pipes closed at one end. So a harmonica is less versatile than a flute. So what do they do to compensate for that? They provide you with many little tubes. Okay. So you can only excite the odd harmonics. Here's a drum head. See that in the strings and the pipes, the frequencies formed a harmonic series. Okay. They were integer multiples. The higher frequencies were integer multiples of the lowest frequency. But for a drum head, you see this is the lowest frequency. They're not integer multiples anymore. They don't form a harmonic series. Okay. All right, so this is the lowest mode of vibration. This is the next higher mode of vibration, and so on. Okay. So let me show you how a drum head looks. Okay, so there's the lowest mode of vibration for a drum head. So when you're learning to play the drum, you're learning where to hit, what spot to hit, and how hard to hit to produce various frequencies. Yeah. Beats, when you play two sounds of slightly different frequencies, okay, what you hear is a sound whose intensity is rising and decreasing. Okay, and so you hear a sound that is its intensity is rising and decreasing with a frequency equal to the difference in frequency. Okay, so for instance, if you play two frequencies, 340 hertz and 345 hertz, okay, you'll hear a sound whose intensity increases and decreases at 5 hertz. Okay. This will happen whether you play 335 or 345. The beat frequency will be the same. Okay. So you'll see that when musicians are trying to tune their instrument, they'll have a tuning fork. That's the frequency they want. They'll sound the tuning fork and then adjust their instrument. If the frequency of their instrument doesn't match the tuning fork, then they hear a beat frequency. And then they're adjusting their instrument tension in the guitar or violin till it matches the frequency. Okay. All right, I'm going to quickly go over some little stuff, fun stuff. Yeah. So here's the internal structure of the Earth. And we've known this only for about 50, 60 years now. Here's how they found this internal structure of the Earth. Okay. Again, okay, how does a wave travel? It travels in a straight line. Is there any way to change the direction of the wave?
Change the material it's moving through?
So it will change direction when its speed changes. Okay, so for instance, you've seen this air and glass. Okay, so here's a beam of light traveling through air, and when it hits glass, in glass it travels much slower, and so it'll bend towards normal. On the other hand, let's say if a beam of light were traveling in glass, and then it hits air, it travels much faster, so it'll bend away from the normal. Okay, you can have two different mediums. If the speeds are the same, then it'll go through straight. Okay, so what's relevant is the speed in the medium. So once the speed changes, so if it slows down, then it'll bend towards the normal, and if it speeds up, it'll bend away from the normal. And this phenomenon is called refraction. And the speed depends on the properties of the medium. All right. So here's how we got this picture. Okay. So an earthquake happened here, and you have seismometers all around the world, and these guys heard the earthquake. So you can reconstruct the path, and this travel like that, and this travel like that. Okay. And you have data from hundreds of thousands of earthquakes, from hundreds of thousands of seismometers. You put it all together, and you can calculate the speed at a given location, which is related to the property of the medium, and that's how you reconstructed this thing, the internal structure of the Earth. Okay, so this was possible only with powerful computers. Okay, a detailed image was possible. So this is a very recent image. Okay. Okay, what does this guy do? You should watch this video on YouTube. It's pretty good. Okay, again, you get sound waves coming in, and these are converted into electrical impulse. Okay. Inside here, okay, so inside the cochlea, there is a membrane that is wrapped around like the cochlea, and see different parts of the membrane. We talked about, remember I said this is a mass attached to a spring, and its frequency of vibration is 1/2 pi over k times m. Heavier the mass, lower the frequency. Stiffer the spring, higher the frequency. Okay, so the natural frequency depends on the properties of the medium. So here there's a membrane that's stiff and heavy and all that kind of stuff, and it vibrates at different frequencies. Different parts vibrate at different frequencies. Okay, so when the sound comes in here, that's passed through that thing, and depending on what frequency there is in this thing, different parts of that cochlea will vibrate, and then that impulse is sent up. Okay.
Do you happen to know what tinnitus is, like specifically?
No, I've heard the term. So here's echolocation. These guys are absolutely amazing. Look at that brain size. That's a pea-sized brain. And this thing can fly through a maze second to none at 60 miles an hour. You watch some of those videos when they're coming out of their caves, there'll be branches, all kinds of branches and stuff like that, and they'll never hit the branch. All right, so they're sending out waves, ultrasonic waves, meaning frequencies higher than 20,000 hertz. You can look it up. I think that depending on the bat, they range, I think, from 60 kilohertz to 120 kilohertz. And we'll come to that in a second. All right, so it'll send out this pulse, and here's the reflected pulse. If this guy is coming toward you, then the reflected pulse is higher than the pulse that frequency you sent it. From the intensity of the sound reflected, you know the size of the object. From the time delay, you know how far the object is. Okay, so this little pea brain is, the data it's getting is difference in frequency. That tells you the velocity of the prey. The time delay tells you how far the prey is, or the object is. and the intensity tells you how large the object is. All that is processed very, very fast. Yeah. All right, what does this got to do with it? Okay, so speed of sound is frequency times wavelength. Okay, higher the frequency, lower the wavelength. Okay, and remember, the size of the object you can see depends on the wavelength. Okay, so the smallest object you can see is roughly the size of the wavelength. So higher the frequency you're using, smaller your wavelength, smaller the bug you can see. Okay, so small bats can live in the same area as big bats because they can see small bugs that the big bats cannot see. So you're not treading on their ground. Okay, so you can coexist with. So this bat can coexist with this bat because this bat cannot see what this guy can see. He can see small bugs, and he'll eat small bugs and live happily. This guy can't see him, and so he lets him be. Okay. So here's noise cancellation. So this is possible because of miniature and cheap electronics. Okay. So here's your music being fed, okay, and your music is being played. But there's sound coming from outside. You don't want to hear this. You just want to hear your music. Okay. So here's what we're going to do. Okay. So here's noise coming from outside. We're going to sample the noise. And then what we're going to do is we're just going to invert this noise. So there's that noise coming, and you play an inverted sound, which is canceling the noise. So this noise is canceled by an sound you produce that was an inverse of that. And then this noise is canceled, and you can just hear your music. Okay. So remember, you had to have a tiny microphone, and the speaker. You already have the speaker, and enough electronics to produce the inversion. Okay, you have two of these sensors, so you can get directional information. Okay, if the frequency is low, then this sound comes here and this sound comes like that. If the frequency is higher, it goes straight through, and this sound is lower intensity, and that's how you tell for high frequencies. We have 2 ears, and localized sound must take different paths to each ear. The head shadows the most distant ear. Sound attenuation is the most effective for higher frequencies. So for higher frequencies, this is how you tell the directional information. For low frequencies, the arrival time difference between the 2 ears is the main clue for localization. Okay. For very low frequencies, okay, again, so speed of sound is frequency times wavelength. Okay, so let's say the speed of sound is 340 meters per second, and you have 100 hertz, then the wavelength would be 3.4 meters. 3.4 meters is roughly the length of those two tables. So if a speaker is playing 100 hertz sound, you don't know where the speaker is within that range. You can place the speaker anywhere there, and you can't tell where the speaker is. So that's why the subwoofers, okay, so your home theater system only has one subwoofer and 5, so it's a high frequency. If the speaker is playing high frequency, you can tell where the sound is coming from. So speakers that are playing high frequency, you now need to have many more of those, so you can have surround sound effects. Yeah. Okay, now we'll understand what this means. Okay, so this is a tuning fork, this is a flute, this is a clarinet, all playing the same note, meaning let's say C note or whatever. And they all sound different, and you can see that the waveforms are different. So what's going on? Okay, so this is a pure tone, but this has harmonic mixtures. So if you break this up, so there's the tuning fork, it's just playing the fundamental. The flute has all these harmonic mixtures. Okay, and you see the clarinet has higher amounts of higher harmonics, so it sounds tinier than the flute. Okay. So here's a violin, and here's another violin. Okay, and they both play C notes. And you pay $1 million for this guy, and you pay $1,000 for that guy. Why did you pay that difference? It's this harmonic mixture that you're after. This guy, the $1 million guy, produced the harmonic mixture that you liked. Okay. In the piano, so here's the A, there's the next A, there's 11 keys in between, so this is the 12th key. Okay, so this key and the next key plays a frequency that is 6% higher. So if this guy played 100 hertz, this guy plays the next key plays 106 hertz, and then the next guy plays 6% higher, and so on. Okay, this guy plays 2 times so 200 hertz. Okay, so that's how the piano keys are arranged. Okay, each key next higher frequency is to the power 1/12 higher. This is the human voice range. Bass frequencies are that. A baritone is 110 hertz to 440 hertz. A tenor is that range. Alto is that. Remember, you can tell a frequency 0.3% higher. Okay. A soprano produces the highest frequencies in that range.